maybe let's do um, as a simple example, we should go over like 20. Sorry, let's start at 20. My bad. I got a little ahead of myself. So 20 is asking us. It's right there. Sorry. I need to print off another one of these. One of them got lost. So this question says, find the global, also known as absolute extrema, on a certain interval. And so I just want to make sure make sure we're all kind of on the same page about what that means. So this is the interval we're concerned with. Okay, so before we get into the calculation, the idea is actually very simple. It's just the idea is really simple. It's just, say you had a function and let's say it looked like that, just whatever. But let's say that you were just looking at the interval from like here to here. Do you see how the global max on this interval would be like here, but the global min would just be this endpoint? So like what that tells us, if you want to find the global max or mins for a function on an interval, basically it's the same procedure. You take the derivative, you look for where's the derivative, 0 or undefined, you make your number line, but then you just also check the endpoints. So I'll just kind of, we'll walk through that process. Do we know roughly what shape this is? Just approximately. Well, yeah, if this was by itself. So if you just had an x to the fourth, it would look like this. But once you throw in more terms, you actually get the possibility of having more like that shape. Does that make sense? So just keep that in mind. It could have some kind of wiggly shape. So if I want to find where does this thing have humps, peaks or valleys, I take the derivative. So derivative of that would be 16. Derivative of that would be minus 16x. Derivative of that would be nothing. That's pretty easy. And then what do I do with that? What do I ask? What question do I ask? Yeah, when does that equal 0? So a little bit of algebra now. So I say, what do I do here? 4x. Yeah, put 4x inside. And now I can see there are actually 3 solutions to this. 0, and then 2, and also -2. Not in any order there. But if I make my number line, 0, -2. Let's test out some numbers. So this is my f prime number line. So I'm testing, where is the derivative positive? Where is it negative? Because I want to know, when's my function increasing? When is it decreasing? That'll tell me if it's a max or a min. Now, a number bigger than 2 would be 3 or something. So positive makes positive. Plug in a number like 1. You have positive times a negative. Plug in -1. You have a negative times a negative. Plug in -3, negative times positive. Polynomials tend to, not every single time, they can go plus, like in the case of a cubic goes increasing, but a lot of the time they go alternating because they're wiggly. So anyway, what that tells us is that the function goes decreasing, increasing. So what that might look like is something like decreasing. Is that dub? Huh? That's the dub, yeah. For the Fortnite dubs. Anyway, This number line, though, you might go, wait a second, is that number line? I don't know about that guy. Is all this, is the whole span of this number line relevant? Yeah, well, this is the interval I care about. I only care about from -1 to 3. So really what I ought to do is take my number line and chop it off. So really I could chop it off right here at -1 and at 3. So it's not even a number line anymore. It's more of a number segment. Make sense? Oh, I didn't erase far enough, sorry. But this is still going to be positive in here. I hope that is clear. Does that make sense?
Yes.
So I know that my graph goes, on this interval, it goes increasing, decreasing, increasing. Okay. So what I got to do now is plug in. I want to figure out what are the actual y values of my function at these critical numbers, these 4 numbers. So in this case, it's not the most pleasant, but it's not the worst, I guess. Let's plug in -1. So basically, we're gonna have an x, f of x, and we're gonna use these 4 values. Does that make sense? Why we're plugging those 4 values in, or? So basically, I'm wondering what's the y value of the endpoints, and what's the y value of these 2 humps? Because this hump, I mean, for example, for all I know, it could look like increasing, decreasing, increasing, but it could just as easily go increasing, decreasing, increasing. I mean, I have no idea really what it looks like. So I actually need to figure out how high are these y values so I can know which one's the biggest, the small, or the least. Okay, so let's plug in -1. A little bit of mental math here. Plug in -1, you get 1 minus 8, -7, plus 7, 0, and let's plug in 0 now. That's a little bit easier. Plugging in 0 gets us 7, 2, a little bit of a pain, but 2 to the 4th is 16 minus 32, -16, plus 7, -9. And then plug in 3. 3 is a little bit more challenging because you got to go 3 to the 4th is 81. You got to go 81 minus 72 plus 7. So that's 9 plus 7 is 16. Okay, so we're okay with that? So it turns out, maybe surprisingly, that all the extreme sort of action is happening right in this little neighborhood here. It goes from its lowest value up to its highest value pretty quickly. And that could be explained by the way these fourth degrees work. You can see basically what happened was it went from, basically went from 0. Not sure what this was, but it went from 0 to 7 down to -9 and then back up to 16. That's kind of the interval we were looking at, some interval kind of like that. Increasing, decreasing, increasing, and it hit these 4 values as it moved. So, okay, so the global max is 16, and the global min was -9. Notice their y values. That's something to make a note of. These are y values. Now, of course, those are the global max and global min on this interval. Make that as clear as possible. That's only on the interval because obviously there's no global max generally because this thing goes to infinity. There's no limit to how big it can get. All right. We'll do 1 or 2 more and then have some work time so you guys can just kind of work on your own. So that makes sense, everyone? Any questions on? hopefully it's not a huge logical leap. It's just, we know how to do it. We know how to like say find local maxes and local mins, global max, global mins. Just if it's on an interval, you just check the endpoints. That's all you gotta do. Just to include your endpoints as part of your alignment. Okay, the question I want to go over with you, it's a very challenging question. It's very interesting though. Can I see one more time? It's this one. Take a moment. Look at 24. I want to know. Take a minute here. I'm really curious if you guys could reason out a rough graph of this. No, don't use any calculus. Just basic reasoning about graphs, things like domain and stuff, domain intercepts. Can you figure out what the graph looks like? And then try to set up, can you find what does it ask? What's the global max or something?
Yeah, extreme.
Yeah, find the extreme. So I don't know, take a couple minutes, try to set it up. Most of the time, we end up with a fairly challenging some algebra, but there's some interesting tricks involved. So anyway, go ahead, give it a shot. Start with a sketch.
What's the difference between a local max and a global?
So a local max, yeah, so a local max is take a basically a cubic function or something. This point here could represent a local maximum because in his neighborhood, like if you like the points to the left and the right of him are all less than him, so he would be a local max. It's like being the fastest kid in your school. Versus a global max. In this case, there's no global max because it goes to infinity, but let's say there was a hump over here. The function was like that. Now, well, for this function, this is a local max and a global max. So this guy is the fastest kid in his school. He's also the fastest kid in the world.
What is that?
Right. So if you're a global max, then you are going to be a local max as well.
That was confusing.
You can get into a rigorous definition like anything in calculus where you talk about what do you mean by a neighborhood, but we don't need to worry about that. It's just you know what I mean by neighborhood, right? This could happen very rapidly too. It could be like a function that goes big things and then like this, even though his neighborhood's really small, he's still a local max, and this little guy, he's still a local min. So you get really
that
small.
graph specifically has like 2 local maxes, 2 local mins, and 1 global max.
Oh, the first one or this one?
That
This one has 2 local maxes. It has 2 local mins, no global because it goes to infinity. Now, if I take this guy and make him say approach negative infinity, now this would be a local. Now there's 3 local maxes, 2 local mins, and also a global max.
and then global mins.
Same idea, like, say that's my graph. This is a local min, this is a local min, that's also the global min for the function. But the problem we just talked about is where you got to be careful is, say I give you a function like this, and you might go, that guy's got no global max, no global min. He goes to infinity and negative infinity. But if I restrict you to an interval, if I say, well, my interval is from this point to this point. Let's say this is the interval that I care about. Well, now this is the global min for this part of the function, and this is the global max. That make sense?
Yes.
So it just depends on the context. Okay, so hopefully you got a chance to start this one. This is one where we're going to have a global max and a global min. which I think is really interesting because, as you go through math classes in your education, you may have noticed they're sometimes ask us for the range of a function, but not that often. Like if it's a really simple function like this, x squared plus 1. Okay, that function you can certainly talk about the domain is all reals and the range is y values greater than or equal to 1. But when you got into functions, a function like this, x over x squared plus 1, you may have noticed that when we covered these in pre-calc, I was often asking you, what's the domain of that function? It's all reals. But I never asked you what's the range. And the reason is because a function like that, you need calculus to figure out the range. So anyway, for this question here, we're going to figure out the range of it. I didn't ask you that directly, but does that make sense how if you know the global max and the global min, then you pretty much know the range? So who has got a graph that they think is correct? Rafe and Jesse, anyone else?
I've got a graph, I don't think it's correct.
Okay, let me see.
It's kind of weird, but I can just.
Okay, it's yours. Okay. All right, let's just so they're both pretty reasonable. They have something in common. Rafe, is that what you drew, or did you also have it? It's curved.
It has, it's constrained between negative root 6 and positive root 6. And then
is it kind of like a curved?
Kind of.
Where's the endpoint? Where's the rightmost endpoint?
I don't know. That was the one part I didn't get.
Okay. So I agree with a lot of your graph, especially these. I definitely agree with this. But there's a problem with anything that has an endpoint like up here. So Jesse's graph, what's your endpoint, Jesse? Where's the 6? Where's your endpoint?
0, or root 6, 0.
Okay. Yeah. So let's combine them too. So Jesse, you got it. It's the graph. You might notice. So if you figure out the domain, kudos. You might notice that x can't be bigger than root 6. Otherwise, I'd have a negative number under the square root. That's no good. So you might also notice that if x is 0, the whole thing is 0. So there's actually 3 x-intercepts. And then if x is positive, this whole thing is positive, so it must just come up and then come back down, and same thing over here.
That's right.
What?
That's what I had.
You had that? Nice job. So this is another good example of one where, this is getting a rough sketch, could be a pre-calculus question, but we again might have asked the question, well, how do you know it doesn't do something really wacky like that?
It's the razor.
Occam's razor. Yes.
Razor.
I know that's what I told you that, guys. Yeah, I told you that for a while. I kept saying it generally speaking, functions will be, once you have sort of constraining factors, you can kind of most of the time safely assume that it's not going to have more squiggles than it needs to have. But I guess there probably are exceptions to that. Anyway, let's actually figure out these points. This will be the fun part. Let's figure out not only where does this occur, so where does this hump occur, and how high is it? And it will also at the same time be showing that there can only be one hump. There cannot be 2 humps. There must only be one. Exactly one. Okay, so let's do the math. The derivative. What rule or rules do we have to use to take the derivative of this? There's 2. Product and the chain rule. Yep, you got to use both. So this is going to employ the fact that, so the product rule, remember the product rule, is A times B. The derivative of A times B is going to be A prime B plus B prime A. And we're also going to use the fact that the chain rule tells us, I'm going to use a specific example of the chain rule, which is that the derivative of root u would be u prime over 2u. So are we okay to proceed?
Yep.
So do we understand why those are both necessary in this case?
Yep.
Hopefully, yes, because product rule, because it's a thing times a thing. That's why the product rule is necessary. Chain rule, because this is not just a simple square root of x, it's a square root of a function of x. So, okay, let's do it. Okay, this is my A, this is my B. So A prime times B. Everyone okay so far?
Yeah.
A prime B plus
Negative 3.
B. So getting B prime is a whole thing in and of itself. Like derivative of root U is U prime over 2. Okay, so again, A prime B plus B prime A, and A was just X. So not easy, right? Anytime you got to use the chain rule inside the product rule, it's always challenging. Okay, so, this thing is a calculus question by itself. To ask the question, so where's my? So let's go over the margin here. You might even take a separate sheet of paper or go in your margin and actually figure out what is the derivative of 6 minus x squared square rooted by itself to figure out. Pretty common for students, calculus students, to do this kind of thing in the margin, to go, okay, that's a thing that I'm figuring out. And that's where you might write out your U, et cetera. So, okay. Kind of gross. So let's simplify it and set it equal to 0. So this guy's already pretty simplified. Now this is going to be the 2's cancel. Then I've got x times x. And I'm wondering, when is this equal to 0? Cool beans?
Yes.
By the way, I don't know, this might be asking you to read my mind a little bit, but do you notice something interesting that this already tells you about the derivative of this? There's one thing. It's something about this neighborhood.
Yeah.
What's happening as x is really close to root 6?
Zero. It's
Close.
approaching infinity.
Infinity. Negative infinity in this case. Yeah, because you'd have an asymptote. If you looked at how does this behave, there's an asymptote at root 6, and so it's actually infinitely steep as you get closer. As you approach root 6, it becomes infinitely steep. That's kind of interesting. But, okay, algebra time. What do?
What?
Can you
Multiply.
or tax like and then times the 6 that yeah.
Like
Third root. The other one. Can you just like subtract an entire thing like that?
from both sides, you could, yeah.
Yeah.
You can make this say this equals negative. Like that works.
And then you multiply by the
Is it okay if I just do it the other way? If I just move this guy instead?
yeah.
So, yeah, it's a great idea. And then multiply both sides by this expression, by this denominator. And it would read, so what's this times this?
6 minus x squared.
If you want to be really Mr. Actually, it's the absolute value of 6 minus x squared. But because x is constrained to live in here to begin with, it's the same thing. This is guaranteed to be positive within the context of what we're doing, so that's fine. So anyway, add that x squared over. Oops, sorry. These last two steps I can gloss over this, right? Look at this answer. Amazing. You get plus or minus root 3. I think it's pretty interesting.
Yes.
Okay, so turns out that this number, this x value is root 3. This one was negative root 3. Now, I'm also curious. Did I phrase the question the way I wanted to? Did I say, what's the global max? Absolute max. Okay, so if a question asks, what's the global max? You can't just say the x value where it occurs. You have to say, would be like if you said, what was the maximum temperature yesterday? And someone goes, 3 p.m. Because that means they misinterpreted. They're telling you what time the maximum temperature occurred when you're actually asking what was the maximum temperature. So just want to clear that up. Okay, so where do I plug this in? Plug it in here? Plug it into the original, yeah. So f of root 3 would be, plug it in there, so root 3 times 6 minus root 3 squared. What does this all come out to be? It's just 3.
Whoa.
That's nifty. That's pretty nifty. Come on, you must admit, confess. Confess. Everyone okay with how that's root 3? Or that equals 3, sorry. So amazingly, this really weird function with weird, irrational endpoints, irrational x values where they occur, the range is actually just a span of 6. Goes -3 to 3. That's fascinating. Maybe not. Maybe it's boring. I don't know. Okay, that's all I got for you
It
today.
is fascinating.
So there you go. Yeah, I think it's a pretty interesting function. But okay, so anyway, hopefully that you got the main idea, which is you can pretty much answer any question regarding where are the maxes, where are the mins, where is the function increasing, where is it decreasing. All those questions can be answered just by taking the derivative, finding where it's equal to 0, and then looking at like when is that derivative positive, when's it negative. So, okay, go ahead and just try to knock out a few on your own. If you have questions and you want me to come talk to you individually, let me know. I can try to answer your questions.